Okay, I think we'll get started. So I will just start kind of by going over chapters 2, 3, and 4. And if any questions come up, just go ahead and ask. And I might be asking some questions along the way. So for chapter 2, it's all just about the basics of mechanisms. So we like to talk about linkages. We can classify them as binary, ternary, or quaternary. This is just the number of connections you can add onto the link. So in 2 dimensions, which is mostly what we're going to be working with, each body has 3 degrees of freedom. You can call it X, Y, and theta, or else you can define these dimensions a little bit differently. So the way you restrict the degrees of freedom, one is a full joint, where you take away 2 degrees of freedom, so there's only 1 degree of freedom left. So whenever you look at a joint, you want to kind of imagine one as being fixed, and then look at how the second one can transfer. So with a pin connection, if you fix the gray, the red can only rotate. Or with the slider, if you fix the gray, the red can only transfer side to side. However, if you redraw the slider, like if it's at a 45-degree angle, you would still say it only has 1 degree of freedom. You wouldn't classify it as like X and Y. You would just classify it as the direction like parallel to the slider. So you kind of have to think in terms of like moving reference frames a lot of the time. So half joints are, you only take away 1 degree of freedom. So that would be something pressing against like a barrier, or a pin in a slot where you can rotate and translate. A gear also counts as a half joint. So kind of what I was saying before, it has 2 degrees of freedom. So it has, if you fix, or I guess if you fix one of the gears, the other one can rotate and translate, but the direction of the motion is always going to be changing as the gear goes around, but it's always going to be tangential. So that still just counts as mobility in one direction, if there was any confusion with that. Let's see. Stone asks if they say it's rolling without slipping, then it's a full joint. Yes, I think that's like in the textbook, that's the 3rd example that they give, but it's kind of it can kind of lead to some paradoxes in the mobility, but yes, that would be a full joint. So are there any other questions right now? Okay, so once we kind of absorb all of the degrees of freedom, we can look at mobility. So there are a couple of different variations. I find that the Kutzbach-Rubler is the easiest. There's just kind of less room for error. So you want to find the number of links, full joints and half joints. So your mobility is 3 times the links minus 1. So you have 3 degrees of freedom per link. And then you subtract 2 for every full joint, since it takes away 2 degrees of freedom. And you take away 1 for every half joint. I don't know if you've thought about the reasoning for this equation before, but that's kind of, it can kind of help you understand a little bit more where it's coming from, and maybe do that a little bit easier. Some other little rules are, if you have multiple links connecting at a single joint, when you're counting joints, you have to count both of those, which I think you've already done some of those in class, but that's just a reminder. Then we get on to isomers. So they're kind of just different ways rearranging a given number of links. So links of different, or mechanisms of different number of links have the number of isomers as follows. So 4, 6, and 8 are somewhat manageable, but then when it comes to 10, that's just way too many to worry about. So the 4 bars you already should be really familiar with. I'll just go over the 6 bars a little bit. There's the Stephensons and Watts. The main difference is just that in the Stephensons or Stephensons, the 2 ternary links aren't connected, and in the Watts they are. And then you can also talk about inversions, which is just grounding different links. So if we grounded the ternary link, that would be 1, or if we ground the middle link, that would be a different inversion. And you had a couple questions on like finding the distinct inversions. So we'll do some problems on that after I just go over the concepts. And then they also talk about transformation. So a lot of mechanisms, you can achieve the same motion in different ways. So this is a cam follower. It'll give the follower basically different range of motion depending on the rotation of the cam. But you can also achieve basically the same motion just with a 4-bar linkage. The Grashoff condition basically fundamentally just determines whether at least one link can make a full rotation. So S plus L, the shortest length, longest length is less than or equal to the other 2 links. So if it's less than, if it's less than or equal to, you can classify it as Grashoff generally. And then less than or equal to, you can make 2 different divisions. So if it's less than, you can have, it kind of just determines the different 4-bar configurations you can have. So crank rocker is basically, you'll have, well, we'll look at some of them later, but you should be kind of familiar with them. You'll just have one link going in 360 degrees and then one rocking back and forth. You've had to make those in chapter 3. The double crank means 2 of the links will be able to go all the way in 360 degrees. And then double rocker is kind of weird. It means the 2 sides are rocking and then the coupler in between can make a full rotation, which I'll talk about a little bit here. Class 2 basically means non-Grashoff, so nothing can make a complete revolution, and they'll only be triple rockers. So when I was taking the class, some people had a little hard time understanding the difference between double rocker and triple rocker because they kind of look the same. You just really have to look at the motion between them. So in the double rocker, in the extreme position, this blue link will basically be making a full 360 degrees between the different toggle positions. And then the triple rocker, between the toggle positions, it won't be able to make a full 360 degree rotation. Class 3 kinematic chain, it is Grashoff. It's just kind of a specific case where it'll only be the double crank and crank rocker. And you can often kind of identify these by the geometry. So they'll be like a parallelogram and have symmetry, or else sometimes they'll be kind of crossed like this. And there are a couple other different different variations of those, but they're a little less common, I'd say. So before we go on to doing some examples, are there any questions on chapter 2? Okay, does everyone kind of understand everything? Are there any holes? Okay. Well, in that case, I will, okay. So I'm just gonna go over some basic examples of kind of calculating mobility, which I think can be beneficial. Let me see. Okay. Stefan, is there anyone who would like to volunteer to try to solve some of these examples? If not, I can at least start with a couple, and then if someone would like to try. Okay, so I will start on part A. So let's just start defining. Okay, yeah, I'll do the first one, then I think Christopher wants the next one. So I just like to start with the ground link first. So it's grounded here, and you don't really call this a link here. Well, you don't classify it as the ground, but basically every ground counts as one link. So we have link 1, link 2, link 3, and I apologize for my handwriting on the Zoom. Oops, that is a 6. Okay, oops. So we have 6 links. Does anyone have any questions about how I counted those? This one should be pretty straightforward. Okay, now I'm going to change the color, and I'll start counting full links, or sorry, full joints. So we have one pin joint here on the ground. We have another pin joint here, pin joint here. We have 2 pin joints here because we have the connection between 3 different links. So 4, 5, we'll call this 6. And then we have our 7th pin joint here. Now, we just have one half joint here, which we'll call the surface, or I guess the connection between this curved ternary link or binary link and the ground here. So you can see here that this link can rotate as well as go side to side. So it has 2 degrees of freedom. We'll call it a half joint. Now we can just write out our mobility equation. So it's 3 times 7 minus 1 minus 2 times, oh, I flipped the color, sorry. There are only 6 links here. That's going to be really confusing. Oops. Minus 1. So basically, we have 15 minus 14 minus 1. So this turns out to have mobility of 0, which means it's not really a mechanism. We just call this a structure. So basically, if you pushed on it, if you applied a force, it wouldn't really be able to move without deforming the members. So you can, that's more for statics. It's more of a truss, I guess you could call. So I will clear that work, and if Chris, you want to give it a shot. You can. I'll let you choose which one, B, C, or D, you want to work on, and if you can, if you go up to, yeah, you can try B. Just go. You should be able to annotate if you just click annotate, and you can draw on the screen. But let me know if you're having an issue with that.
Can I use my mic? Is it okay?
Oh yeah, go ahead.
All right. So it has 2 grounds, right?
Okay.
That's a thick line. There we go. So 1, 2, 3, 4. Okay, so 2 of those. There's no links, right? Or, well, I guess if it doesn't have a pin, it's not a link, correct?
These are still considered links.
Okay.
Yeah. So, well, okay. So Stone is asking, wouldn't both grounds be one link? So there are a couple of different approaches. I guess the different equations. So what equation are you thinking of using, Chris?
I was gonna just go with the Kurzbach and then give that a shot, but I don't think that's the right one for the scenario, because I think that's gonna give us either 0 or I feel like it's still gonna give us 0.
Well, so in this case, Stone is right. You just count the ground as one link. So
Okay.
in one of the equations, you measure like the number of grounds, but the Kurzbach kind of simplifies that. So I just want you to kind of picture if you have a binary link, if we just like put a link here, it's I think you can kind of see what I'm saying. And then basically you just ground this link, or you make it fixed so you can't move it.
Okay.
That would be the same thing as having 2 separate pin joints, right? And imagine these cams like they don't contact it or something. Imagine they're like in a higher plane.
Okay.
That would be, if you just have a fixed binary link, that would be the same as 2 pins like that. Okay.
Okay.
And
so then,
yeah, so go ahead.
so because it's their fixed locations, this would act as that, because they're fixed, they act as a link.
Yeah, exactly. And even if you have more than 2 grounds, you can still, everything counts as one link, because like let's say we have, I don't know, we have another ground here. You can still just draw like a triangular link and just call it fixed.
Okay.
Yeah. Okay.
So only until there's a separate link, kind of like here. That so the fixed locations are their own link, and then anytime there is not a fixed location, just a contact, that would just be a
Yeah,
joint
I mean,
rather than a link.
I guess technically you could still call it the ground. The joint that we're looking at in the place you highlighted is really between the gray link and the ground. That part doesn't really matter. It's kind of just like the limiting motion. Like if you look and see, you have like the walls of the cylinder for the piston. It's kind of
Right.
just limiting the motion. It's not really a link or anything. You can just kind
Okay.
of consider it as part of the fixed ground. Okay, so knowing that the 2 grounded links count as one link, do you want to count again? See what you get?
Yeah. There we go. Okay, so it's one link and then no full joints and two half joints.
Okay, so you do have some full joints there between the cams and the ground. Can you see that?
Okay. Yeah, so each of these pins here.
Yes, each of those count as a full joint.
Okay. And then because they make contact with each other, that would be one half joint.
Correct. So how many links did you come up with again?
Two.
Two.
Or sorry, one link, two full joints, one half joint.
Okay, so we counted the link of the ground, but I think you're not counting the links of the cams that are contacting each other, because those also count.
Okay, so this whole both grounds count as one link, and then the link is the cams also touching each other.
Each cam basically is a separate link. So if we just redrew this a little bit, how I was saying a little bit, we can make like transformations. So if we have, how do we do this? It's going to kind of cover each other, but let's say we have the cams kind of coming out like this, and then this is where they meet. You could kind of redraw this cam connection as like a 4-bar. So cams are a little tricky, but I think you're getting the hang of it now. So we have two half joints, right? I mean, sorry, one half joint. So can you do the mobility equation really quickly and see what we have?
Yeah. So we have two links.
We have how many links?
I'm sorry, three links. Three links. Nice. Then we have 2 times, so 3 times 3 minus 1, minus 2, minus 2, minus 1, gives us 6 minus 4 minus 1, which equals 1 degree, or 1 degree of freedom, or a mobility of 1.
Correct. All right. Very good. Thank you. Would anyone else like to try a problem?
Yeah, can I try C?
Sure, go ahead.
All right, so for the links, there'd be the one link for the ground, plus 2 would be the circle, 3 would be that white connector, and then 4 would be the red square. So it'd be 4 links.
Okay.
Or joints, or 4 links. And then for the joints, you would have the one in the middle of the circle, then 2 to the left of it, 3 on the red square, and then would 4 be like the piston assembly, right? Or like the inside?
Yeah, 4 would be
So,
this
like
just
the
it's just a
walls.
slot. Well, it's just a slot connection. So like
Yeah. Wait, that's what I meant. Yeah.
yeah, so if we redrew this as just like a slot.
Right. I like in D, like that, or not. I guess it's not like that actually.
Yeah, indeed, it's actually a full joint, but like the
Right.
sliders in the examples above,
Yeah.
it's just like that.
Yeah.
So actually,
Yeah.
let me
Okay.
just
So
mark it out.
okay. So 4 links and 4 joints come out to 1 degree of freedom.
Okay. Very good. So let me just draw these out so we'll also have this on the recording. 3 full joints, so our mobility ends up being 3 times.
Is there 3 joints or is there 4 joints?
There are
'Cause I
4.
put 4.
Yeah. Sorry, there's the pin between the
Yeah.
connecting rod and the slider, and then there's the slider in the ground.
Yeah.
All right, sorry. Okay, thanks, Michael. 4 minus 1. So basically we have all right. 1, 2, 3, 4. Yeah, so we have 9. What am I looking at here? Times 2. We have 9 minus 8, which gives us 1. Okay. Kind of slow just drawing on Zoom, unfortunately. Now, would anyone like to tackle D? Oh, sorry, Thomas has a question. Yes, it's considered, so it is a little hard at first to wrap your head around. So yeah, this is considered a slider. It's a full joint because this block basically can only translate up and down. And all you care is the connection between this block and the ground. In part A, it can translate as well as this thing can rotate. Anyone like to work on D?
I can take it.
Okay, cool. Did you say Massimo or Massimo?
Massimo.
Massimo, okay. Go ahead.
Do I have drawing permissions, or is it just
Yeah, you
should
should be able to press annotate if you want. Should be at the top, I think.
Oh, yeah, I see it. Okay. So we have this ground. Sorry. We have a ground here and a ground here, so that's 1.
Okay.
I'll write my G. And then this would be 2, 3, 4, 5, 6. And one question I did have about this is, would we consider this pin and slot as 2 links or as 1 link? Because I considered it as 2 because of how the math worked out, but
you're talking about just the white piece at the bottom, right?
yeah. Is that like its own thing, or is that maybe part of the ground?
So how did you see it as part of the ground?
Well, I didn't see it as part of the ground. I considered it as a link.
Okay.
But I considered it as 2 links because of just how the math came out. But I'll consider it as 1 link right now.
Okay. That's interesting. If you wanna, I've never thought of looking at it as 2 links. If you wanna.
Well, I mean, not in like a conceptual way, just of like how the math turned out.
So you're saying like the answer you got, it had to count as 2?
Yeah.
Okay.
Unless I used the wrong equation, it's possible.
Okay. Well,
because I didn't consider half joints if there are any in here.
Yeah, let's just keep going and see what happens. Oh, so Stefan is asking if there's such a thing as a half link. I don't think so. A link is a pretty physical thing, so I've only ever seen them counted as 1. Okay.
So I thought if it could translate and rotate, doesn't that make it a half link?
You mean a half
I
joint?
think that's half
Oh
joint.
yeah, sorry, half joint. That's what I meant. Half joint. That's
Yes.
okay. That's what
Yeah. Yeah.
So then this is a half joint then.
Correct.
Okay.
Let
So
me,
if that's a half joint, I'll just write H there for half joint. And then J, right? I don't remember the
yeah, just
notation
yeah, that's good.
for joint. And then, so this would be for full joints, right? So
Yeah.
there are 5 full joints and then 1 half joint.
Okay. I think I see you're missing a couple full joints here.
Yeah.
Look at
Oh,
the ground connections.
yeah. 5, 6, 7. Sorry.
No problem.
And that becomes 7.
Okay.
So then that's 3 times 6, which is 18, minus 2 times 7, 14, 4, minus 1, so 3.
Yeah. Yeah. So you get a mobility of 3 for this equation.
Yeah, I have no idea. On the homework, I have no idea why I did that. It was because I was using the wrong equation. I completely forgot about the half joint
Yeah.
expression. So,
Yeah.
yeah.
So some of them, I forget the name of the equation, but you subtract like half, or you subtract like 1 for a half joint.
Yeah.
And that one's just a little bit more confusing. I like the Kutzbach Grubler that I included. It's just a little bit harder to make mistakes with.
Yeah.
Okay.
Thank you.
Yes, you're welcome. Does anyone have any questions about what we just did?
I do have a quick question. I don't know if you want to do this now or we can do it later, but in the homework for 2.21, some of them there was different answers for what you posted versus what was in the book, and I was curious like which would be the right answer if it was came up on the exam. Like for one of them, I think it was like I think for E it was like in the book it said -1, whereas the answers you posted it said the mobility was 0. So I wasn't sure which one would be the correct answer.
You said that was 221?
Yeah, I think it was 2.21, and
Okay.
we can do it later if you want to keep moving.
Yeah. Let's look at it in just a little bit. I see in the chats Thomas has he's saying 8 full joints. So where do you see where do you think we're missing an 8th joint? You can either type or voice chat. Full. Well, if you're 8 full. Okay, so we counted, I'll just go over it again. 1, 2, 3, 4, 5, 6, 7 full joints. Where were you counting the 8th one? Yeah, this is the half too. Okay. Cool. So I think we're all good on that. Let me clear all drawings. Okay. Grashoff condition should be, I think it's a pretty simple concept, but We can just go over a couple questions of that too. Would anyone like to crunch some numbers, or should I just do it? Okay, I'll do this one. Yes, so Stone says, so S plus L, we have short plus long is 150. And then the remaining two are, again, just 30 plus 150. So and we would actually classify this as class 3 because it's equal to. And if we draw it out, we can kind of see the parallelogram here. So kind of what I was talking about earlier, you can look for symmetry. And if we wanted to, you don't really need these disks. You could just make a little link and just a simple 4-bar. Okay. This one is another mobility question. Anyone want to tackle those? Those you kind of need a lot of practice. So this is just another good opportunity if someone wants to go. Okay, Stone's got this one. Feel free to write or whatever. So it looks like he's counting joints. So he's got 7 full joints. No half joints. Six full joints. I mean, sorry, 6 links. Okay. So that gives us mobility of 1. All right, thank you, Stone. Anyone have any questions on that? Good, okay. And now, oops. You guys had some questions like this, I think, on your homework. So I like to just kind of go over finding distinct inversions of an 8-bar. So does anyone want to share their method of solving these questions?
Yeah, I can.
Okay, go ahead.
So what I do is I pretty much count the links individually, and each of the ones that would say be symmetrical, I would combine as one. So for example, for inversions for this one, I'd count 1, and then I'd count 2 and 4 as 2.
Okay, good.
And then 3 would be 3. And then 5 and 7 would be 4. And 6 would equal 5. And then 8 would equal 6.
Okay,
Right?
yeah,
So,
perfect. So you kind of just have to go through by symmetry. Just here, you can kind of draw the symmetry plane down here. So if you're able to have a link that is just the same thing on the other side. Well, sorry, I guess my Zoom crashed. Still recording. Okay, so yes, exactly what Michael said. Just kind of go through the symmetry, make sure everything's.
Would you mind repeating what you did?
Yeah, so just kind of, I like to go across the 8 bar and just start counting links, but then you also kind of have to see if each link could have a symmetrical link, like if you could draw a line of symmetry and it'd be like the same thing on the other side. So this 8 bar is kind of straightforward because you can just draw a line of symmetry down the middle. So you can see 5 and 7 are the same, 2 and 4 are the same. You can't really draw like a horizontal one because they're not perfectly symmetrical. So I'll just go through. I'll count link 1 as 1. I'll count link 4 as 2. And if we look over to link 2, fixing link 2 would be the same thing as fixing link 4. It would just be basically mirrored. So 2 doesn't count as a separate distinct inversion. 3 will count as another one. 6 will count as another one. Since these are kind of on the line, you can't find a mirror of that. 7 counts as 1. And if you look across 5, if you fix 5, it's the same thing as fixing 7. So that doesn't count as another inversion. And then link 8 is again just another one, another distinct inversion. Is everyone clear on that, or would we like to do another one of those? Okay. Okay, so if you want to look at some more of those, there's like a table of all the different 8 bar, basically 8 bar configurations in the textbook. You can just look at those again, but once you kind of know what you're looking at, it shouldn't be too difficult.
Actually, I do have a quick question on this one.
Sure.
So if let's say like 2 and 4 were like it was like exactly the same, but 2 and 4, maybe like 4 was like way bigger than number 2, would that still be symmetrical? You know what
Yeah.
I'm saying? Would it still count as?
Yeah, sorry, that's a good thing. It's not symmetrical as in size, it's symmetrical as in like basically the type of link. So
Okay.
as long as there's 3 connections and they connect to the same thing, it doesn't matter really the size of the shape.
Okay.
Okay. I guess let's just look really quickly at, I think Michael said it was problem 221, and you're talking about like the solution files that I sent out over web courses, right?
Correct. Yeah. So for I think it was for maybe it was E, and for H there's different. It was kind of different in the book versus your solution. So E in the book says it's -1 for mobility, and that's a paradox. And then your solution says that it's 1. So I was wondering, like on the test, which one would be the correct answer?
So you're saying in the book it gives H -1, or what is it?
Yeah. So let me check again. So in the book, the mobility for E in the book is -1. And it says it's a paradox.
I don't think you'll really have any questions that are paradoxes on the exam, just because the nature of like a question having two different answers is kind of hard to ask.
Okay.
But looking at these solutions, at least for E,
Yeah, I understand the explanation that it gives. It's saying because like you get rid of the redundant links and then you calculate it that way. But I was just, like I said, I wasn't sure which one was the right answer because, like I said, the book gives one way and the solution manual gives another answer.
yeah, I think that's kind of tricky. I think these solutions come from the solution manual. I don't actually know where these came from.
Okay.
But you know, it's possible that either the textbook or the solution manual could have the wrong answer.
Okay. I could ask him in office hours later. That'd
Yeah,
be better.
yeah, that might be better. It's kind of weird with the paradoxes.
Yeah.
Kind of just shows that sometimes it doesn't work, but
Right. Okay.
okay. In that case, if no one has any questions on chapter 2, I'll go over chapter 3. Okay. Can everyone still see my notes? I think I am.
Yep.
Okay, thank you. So chapter 3 is mostly drawing based. So I know you should have kind of done these questions by now on your homework. However, this test won't really require you to like draw stuff and upload it. I believe Dr. Nader is having his own drawing test in, I want to say July 7th, excuse me, sometime around then, which you'll need this more. But it is still good to have the knowledge for then, and it might come up as some conceptual questions. But I think it's pretty safe to say that you won't have to like draw this out and upload a picture of it for your exam. So I'll just kind of browse over these kind of quickly. I won't really go over the construction like steps because they're pretty straightforward. I'll just kind of go over the conceptual differences between a couple of the different mechanisms. So this is just a basic rocker. So we call this a function generation because we're just looking at the movement of a point. So we want B1 to B2 just back and forth. We don't really care about the link 04 B2, just position to position. So we have our crank with this little piece. We have the rocker. Can you guys actually see my mouse, what I'm pointing at?
Yes.
Okay. So those are the important parts, the crank and the rocker, which you should be familiar with. And I guess I'll say it again. The crank just means it can make a full circle, and the rocker means it's just rocking back and forth. It's never gonna make a full rotation, no matter how many times you spin this thing around and around. So you should know, you should have done, I think, at least one question like this so far. The other type of rocker motion, it's a motion generation. So we're looking at moving an entire link from place to place, which you could basically simplify into a bunch of different points moving from place to place. But basically you do these 4 steps first, and then you go back to these steps to finish it off. The coupler output is one of the more interesting ones, I'd say, I think you guys worked on this in your homework. That was one of the harder questions for chapter 3. Something like this should look a little familiar. Moving the coupler from position 1 to position 2 and back, just making a 4-bar.
Yeah, I think that was problem 3 in the homework for chapter 3.
Yes. For that question, you also have to do adding a dyad to make a 6-bar. That's I actually didn't copy that into my notes here, but it's really, there's just another section for it in the textbook, and you can just follow the instructions from there. And I'll actually go over that question, so we'll see it there. So a quick return mechanism is basically, it's just a rocker, except it has uneven rise and fall time between the toggle positions. So here, when we're generating the rockers, because the crank is basically in line with the line you draw between B1 and B2, it's like, I don't know the right, it's like a time symmetric motion. So you could turn this into a quick return mechanism. Basically, all you're doing is you're changing this angle. So if you make your crank here, and it's just attached, not in line, that's a quick return mechanism. And then the equation is just kind of determining how quick returning it is. So we define the time ratio as, okay, alpha over beta. So like I said, instead of drawing it out normal like that, you're drawing the connecting rod out at an angle, excuse me. So if you finish these lines, you'll see you'll have your alpha angle and your beta angle. So because they're different, it's going to change the timing. If it goes out straight like that, then basically alpha and beta will be the same, and you won't have a quick return mechanism. Equal time interval. The time ratio is pretty straightforward. You just divide alpha by beta. So usually in a question, they'll give you the time ratio, and you'll have to determine alpha and beta from that. Okay. And then coupler curves. Some people were, again, coming into office hours because there was a question, I think, on chapter 3 homework about finding the coupler curve, which you can't really do by hand. You kind of have to do it with a computer. Excuse me, sorry. So the most we can do really is just kind of examine the coupler curves and find some interesting data from them. So we call the cusps as basically these limits where it changes directions. So your mechanism will have, or the coupler will have 0 velocity at that point. So it's more helpful, like practically, if you want to, like if you're on an assembly line and you need to move your product from here to here, and then like pick it up with another mechanism and move it from here to here, you want to make sure that happens at the cusp. And then crew node is just where the coupler curve crosses itself. That's a little bit harder to define like a practical application for. Maybe you just want to like look for, make sure your mechanism won't come into contact with itself. I don't know. But basically, there are these atlases that have just like thousands of different coupler curves. Oh, Michael CC is asking, we can just trace what you think the coupler curve will look like. I honestly don't know what to tell you for that one. If you can make it in some sort of CAD, that would be ideal, because it's kind of hard to see what the coupler curve would look like without some sort of CAD representation. I kind of like drew it out in SolidWorks. I just drew a bunch of little lines, dimensioned them, and then spun it around and saw what happened. That made it a lot easier. If you're not familiar with a CAD like that, then just kind of do the best you can, I'd say. So yeah, then just tracing it out, I guess, would be okay. So you usually, you'll come into, if you're designing a mechanism, you'll have like a type of coupler curve in mind that you want to achieve. And then the atlas will basically give you the lengths of your linkages to get such a coupler. So it kind of works the opposite way of generating the coupler curve. You kind of generate the lengths of the links from the coupler curve that you want. Stefan's asking if there'll be anything on coupler curves on the exam. I don't really know. Oh, on the drawing test, I would say probably not. It's really hard to do without a computer. Maybe just a conceptual question about like cusps and crew nodes, because that's a little bit easier to ask. Or maybe he might ask like, what kind of coupler curve would be best for something like this? And then maybe you just have to identify the one with a cusp, like at a certain point. I'm not exactly sure. Christopher says you can use cardboard. Yeah, if you wanna make a cardboard model, that works too. And Massimo says you can draw it out on paper too, but it does take a very long time. Cognates is again just kind of a conceptual thing. I don't think you'll ever really be, well, at least on this exam. I'm not sure about the drawing exam. I really don't know anything about this exam yet. Cognates are just different ways of making mechanisms or linkages with the same coupler curve. Just kind of interesting concept to look at, I guess. So a lot of chapter 3 is either drawing or conceptual. So just a couple other useful mechanisms. The straight line mechanisms, historically really important. Like in the steam engine, you can see this link 3 basically rotates and goes up and down. So if you attach a bar to the center of link 3, when you turn this wheel, this plunger will basically just go straight up and down. But modern day engines and stuff, they have different ways of doing this. It's kind of just like a historically significant mechanism, I guess. So dwells are basically just points in the coupler curve in which part of your mechanism is stationary or almost stationary, because usually these dwells, none of these, like a lot of these straight line mechanisms and dwells aren't perfectly straight line or perfectly dwell positions. They're just like really close, because it's hard to turn like rotation into straight lines and stuff. So dwells again are just kind of useful in designing machinery. So like if you can look at this coupler curve here, when the crank turns and this connecting rod goes from point P to point B, this piston will basically be in about the same position. Okay. Does anyone have any questions before we do some examples?
Adam, I have
Yeah.
to leave for the dentist in a minute. Where will you be uploading these videos or this video?
It'll be on web courses and modules. I think Dr. Nader already made a new tab. I think it's called Atom. So I'll just
Okay.
be uploading. I think I'll just upload this to YouTube and then attach a link to it or something embedded in.
Okay, thank you.
Yeah, no problem. It should be up today. Okay. So this is, I think, basically the question you had on your homework. So you want to make a linkage to go from, let me choose a different color, this position to this position. So scrolling back up, looking at a couple of these different mechanisms, we're looking, this kind of looks like what we're looking for, right? Moving a coupler from one position to another. So this is my solution for the problem. I just redrew it on paper. I tried to make it kind of to scale, I guess. So we have our linkages. These are our desired coupler outputs. So what we want to do, you're just kind of drawing your bisections between your C's and your D's. And then, oh, I guess not your bisections. You just draw your connections between your B's and your C's, and then you make your bisections. And then in the question, it says to make it connect to the base. So we'll just stop there at the base. So now we have our O2 and O4. These are just kind of, I guess, our ground positions. So now if we're just doing a very basic coupler, we can just draw our arms. So this would be, in green would be position 1. As you can see, I kind of drew it out here, and then it's confusing to draw everything all over each other. If we take, I don't know, pink, then we move our links to this position, and that's basically the second extremity. Did someone have a question or no?
I'd say for this kind of drawing, is it a little bit arbitrary, or we can, if we didn't draw this like method, we could, as long as the mechanism technically accomplishes the point, then
Yeah, especially for like adding the dyad, there are a lot of different ways of doing that. For the 4-bar mechanism itself, I don't know that many different ways of doing it, unless I guess maybe if you put your points farther back on the base. But okay, so now that we have those positions, there's a section in the book basically about adding a dyad onto a 4-bar to make it a 6-bar. So let's just draw, let's do a different color, sorry. Let's just worry about this top link of the 4-bar. So in position 1, it'll be here. In position 2, it'll be here, right? So we need to add a 4-bar, sorry, add a dyad to limit its motion basically from C1 to C2. Now, the approach I took was turning this link into a ternary link. Basically, it's just useful because you can kind of offset a little bit where your dyad is going to be, because if you make, if you just add the dyad onto your link, then it's probably going to end up being like vertically like down here or something. So adding on a ternary link gives you a little bit more freedom to change where it is. So technically it makes it a little bit trickier because you have to do a little bit more geometry. So this angle is equal to this angle. And then your bisection of that angle is, or the bisection of that distance is going to equal the radius of your crank. So I know that's kind of a lot. Are there any questions on this? Okay. In that case, here's just another example of drawing a quick return mechanism. The specific instructions you can find on web courses or in the textbook, but I'll just kind of go over some of the geometries here. So you have your beta and your alpha. Oops. And then your delta here is, I think, the difference between them. No, what is delta? Oops. Delta is, I don't have the equation for it. I thought delta was the difference.
I think delta, hold on, I just wrote that down yesterday. Delta's B minus 180. Oh wait, no, just kidding. I think that's right.
Yeah, it's 180 minus alpha. So, yeah. It's just kind of a geometric. Yeah, and your alpha and your beta, again, are kind of interchangeable, I guess, just as long as, because the motion is going to be the same unless you need to know its quick return, like advancing or returning, I guess. And then that again depends on which direction your crank is rotating in. So Massimo is asking how we determine drawing the first link, which I believe he's asking like this link. Is that correct?
Yeah, so basically, when I was doing this problem, I would like choose an arbitrary, I'm gonna draw real quick. I would choose like an arbitrary angle. So like, I know it's supposed to be 25.5, but say you started off by drawing this link here. I was finding myself just kind of like through trial and error getting my next like position to pass through like this line here that continues off with like the protractor. Like I'd put a point down, put the protractor, see if the line would pass through, and then move down the protractor and keep doing that until it passed through. So is there a better way of doing that?
So you might want to, so you are basically drawing an arbitrary line, but it might help if you measure the angle of the line that you're drawing. So like from horizontal, I don't know,
I see.
measure whatever angle that is.
Okay.
It doesn't matter what the angle is, just you're going to take that angle and then you're going to basically subtract your delta, and then whatever that angle is, that's like mathematically, I guess, the faster way of doing that.
Okay. Yeah, that makes a lot more sense. Because, oh yeah, I see now. Yeah. Okay.
Yeah.
Thank you.
Yeah, no problem. So yeah, I guess we kind of just said what to do next. So you kind of draw that link out at an arbitrary length. It's probably best if you measure the angle, and then draw out your second position at an angle of delta. And then you're just doing the same thing as the other rockers, where you find your bisection. Well, actually, no. It's a little bit trickier. I think you are, yeah, it's a little hazy for me, I guess. I think you extend B1 to B1 prime. And then I think you find the bisection of B1, B2. Yeah, and then half of this is going to be the radius of your rocker. So again, pretty much I feel like if you just kind of follow the drawing instructions, it's usually pretty straightforward. Just looking at some of the angle stuff, going over some of the angle stuff might help you a little bit. Are there any other questions on that? Yeah. Okay. So I posted the.
Actually, I do have a question if you don't mind.
Yeah, go ahead.
Would you mind proving that the distance for your B1 to A1 is the same as your B2 to A2?
Oh, so you're saying this and this? Man, that's a tough
Right,
question.
because there you're accounting for the crank itself, not just the coupler. But for the B1A1, that's just the coupler. You're not including the crank, so it's not the same distance.
Well, that's because the crank is like collinear with the connector, with the connecting rod. It's like underneath. And actually, let me draw it in a different color. So let's say blue is the crank. So yeah, that exactly, they overlap there. So basically the crank goes out this way, and then the connecting rod comes from point A out to point B. And then here they're like collinear but extended.
Okay, I see it now. Thank you.
Okay, no problem. I don't know. I'm sure there's a geometrical way of proving the similarity and like how it's the angle there. I've never really calculated that out. Okay, so I think for the sake of time, it's better for me to go over chapter 4 right now, because I think it's a little bit more applicable to the exam since it's not just drawing. When we're done, if we want, we can go over some of the chapter 3 questions I posted. But I think chapter 4 is good for now. Does anyone disagree with that? Okay. Oops. Okay. Don't know why this is all blue. So chapter 4 is all just about motion, calculating mostly position. So we're saying that complex motion can be described as the sum of translation, which is just like this link moving from one position to another, and then it rotating. So here we can do translation and then rotation. And if we add them together, we get the new position. Which I think you should be familiar with from dynamics and stuff. Okay, so I'd also been getting some questions about like open and cross positions. So often 4 bars will give you this theta 2 angle here. However, For some configurations, there are basically two different positions of links 3 and 4 that can satisfy that theta 2. And we call them open and crossed because it's pretty intuitive, because one is open like that, and then the other one, so open as in none of the links cross each other. So you basically have, if you like shade it in, you have a solid area. And then your other position, so remember, same theta 2, so your link 2 is in the same position, but then your link 3 crosses your link 1. So it's crossed. You don't have a constant area. Okay, so the algebraic method that they introduce, it's good for finding like the positions of the nodes here, which would be like your AX and your AY, which would be the X coordinate and the Y coordinate of A. Your B is the length of link 3, C is the length of link 4. And these are just some really big equations. Not really big, but they're kind of just a pain to go through. But I think they're pretty straightforward too, of just calculating the different positions. So the other strategy, the vector method, isn't as good for finding like positions of the links, but it's good for finding the lengths. Even though the algebraic method, you can find some of the lengths there. But the vector method specifically will be used more in chapter 5 when you're finding the velocities. Just, you know, like your R omegas basically. So knowing like the X and the Y coordinates of the vector that represents your link. Anyway, these equations, basically all these equations are going to be given to you on the exam. They'll be on the formula sheet. Just kind of be familiar how to use them, and kind of like what I was saying with the algebraic being good for node positions and the vector being good for lengths. If you're looking at a problem, just kind of be familiar with which equations you might want to use, because otherwise you might get stuck. So again, these k values are kind of just constants that you use to solve. And then you can solve for your theta 4s and then your theta 3s. Basically all these things, you're given theta 2 and you're solving theta 3 and theta 4, and then maybe the lengths or positions of the other links. So the crank slider, so crank slider and slider crank are a little bit confusing, but they're basically the same thing, which I'll go over. So in the crank slider, you're given the theta 2 value. So basically you're writing the problem as a function of the position of your crank. So here are just some more equations for finding the theta 3 angle and the distance d. Oh, this is another good point. So d is not actually, there's no link here. It's just the distance between the center of the slider and your origin here. So if you actually draw it out with like the links, there's only, it's only like this, and then it's sliding on the ground. So your D can change depending on the position of the crank. Again, just kind of plugging it into the equations. So the slider crank is exactly the same geometry as the crank slider. However, basically you're given the distance d. So you could say, like, instead of rotating the crank, you're driving the slider, and you want to find, oh, Stefan is asking, is theta 4 always 90 degrees? Yes, if the ground is horizontal, basically. They could, I guess, technically give you a crank slider where it's translating like this. In that case, your theta 4 will be, it'll still always be the same, but it'll be, you know, whatever that angle is. Generally for crank slider, it's just going to be 90. Yeah, I don't think they're going to give you anything super complex like that. So slider crank, basically you're given, they say the input is the slider, so you're given the D and you have to calculate the position of theta. Which slightly different equations for your theta 3s, but you can still use the D equation here because it's the same geometry. They're kind of just rewritten so you can find the thetas without theta 2. Okay, inverted crank slider. So remember how we were talking about inversions? Oh, offset. Someone's asking about offset having to do with C or R4. Yeah, usually I believe when they say offset, they mean this angle, or sorry, this measurement here, the C, just the distance between whatever your slider's sliding on and like your ground. So the inverted crank slider, so you're basically just grounding. Now you're adding, and you have 4 links again, and you're grounding this bottom link. And you have this slider that's going to be constant radius from 04. So basically it can do this motion. So the link B is going to be rotating, so it's always like 90 degrees with the slider. This kind of has its own equation for finding the angles. I guess usually you'll be given your theta 2 again, and then you're just solving theta 4 and theta 3. So this is kind of just vector. It's really just vector addition. So once you solve all the positions, if you know, like if you want to find the distance of P, it's kind of can't see that. If you want to find the distance of P, you can do vector addition of the radius of A and the radius of PA, which again, you should probably be familiar with vector addition. We talked a little bit about path function and motion generation. They're kind of just conceptual things. Path generation is just the point. So like we were talking about the very simple crank rocker, you just care about the point from rocker position 1 to rocker position 2. The function is just kind of the relationship between your input motion and your output motion. You care about this more, I think, for like if you want to make if you're designing a mechanism and you want a specific output, you know, what input do you need to get that output? And then motion generation is basically path generation, except it's 2-dimensional instead of 1-dimensional, or 3-dimensional instead of 2-dimensional, I guess. You're moving a line from place to place instead of moving a point. So I guess you're moving a line in 3D space instead of a point in 2D space. Okay, transmission angles. These are something that we should review because I think these are pretty easy questions to ask on the exam. So The transmission angle is basically just you take your links, back color, you draw your links out like this, and then whatever the angle between those two links is your transmission angle. Generally, you want larger transmission angles instead of smaller transmission angles because you're kind of like concentrating stress with a smaller angle, and it's easier for things to like lock up basically. So a lot of this depends on the Grashoff condition. So if it is Grashoff, so they can rotate like this fully. The okay, so I guess the toggle positions are, I guess they're not toggle positions. The minimum transmission angle is going to be found when your crank is in one of these two horizontal positions. So you kind of just have to draw it out in the two of them and do the math. So the transmission angle, which is your, I guess, the gamma here, is really just as simple as your theta 3 minus the theta 4 absolute value. So once you've solved your problem, well, I guess once you set it up in that point, you have to solve for theta 3 and theta 4, and then subtract them if it's a Grashoff. And then this is just saying, basically, just kind of like look at the angle, and if it's like 180 degrees more, just subtract it. Or I guess that's 45 degrees. Why is it that? I don't know. Most of the time when you're drawing these things out, it's best to, well, when you're calculating these things, it's best to draw it out to make sure that what number you got makes sense, because sometimes these geometric equivalencies don't really equal like physical equivalencies. So it's good to just double check. So non-Grashoff 4-bar linkages are a lot easier to find the transmission angles, specifically at toggle positions. So since they're non-Grashoff, the whole thing is they can't make a full rotation, right? So the maximum limit of their rotation is called a toggle position. So again, so like if your rocker is in this position, that's as far as it can go without going in the opposite direction, where you'll get to this position, and then it binds up basically just from the geometry. So with a non-Grashoff 4-bar, in the toggle positions, it basically ends up being a triangle. So you have your link here, and then you have your two links here that are basically in line. So you can just add up the lengths of those links and solve it just with law, or with the cosine law. There are some equations in the textbook that are basically just like a modified cosine law, but at the most basic level, just use law of cosines. Okay. Does anyone have any questions on that? Or I guess we can read over a couple of questions. Okay. Does anyone have a preference if we go over chapter 3 or 4 first? I'd say chapter 4 just because we've done some of the 3 already. Stone says 4. Let me pull up some questions. Stone's asking if we could do an inverted crank slider. Let me find one. Is this problem okay? It's an inverted slider crank, but like we were saying, the crank slider and slider crank are kind of the same thing, just one you're given theta 2 and one you're given d. Does anyone have a problem with that? Okay. Let me see if I can pull up. So this is one of the questions where they just give you the different dimensions and you have to draw it out. I think you probably had a question like this on the homework. So they'll give you A, C, D, your theta 2, and your gamma. Okay, so what is the goal here? Just find theta 3 and theta 4 for the open and closed position, and vector RB, which let's just focus on theta 3 and theta 4 right now, because that's the R vector is more it's kind of a different problem. It'll take a while. Okay. So your gamma here is 90 degrees. So let's just draw out. Oops. You have your link. I guess this is your link 2. If you call the ground link your link 1. That's true. And then that's your other link. I guess I should have done those in different colors. So we're given theta 2 is 30 degrees. So we know our theta 2 is in this position. However, now we want to know the 2 different positions. So like we were saying earlier, we know we can either have open position or I think it'll look something like this, or your cross position. So theta 2 is the same, then we just want to know our different do a different color. This would be our theta 3, theta 4 for the open, and then color again. Pretend that line is horizontal. That would be our theta 3 crossed, and this would be our, well, yeah, this would be our, I think that's our theta 4 open. No, I think I drew that wrong. You want to draw theta 3. Sorry, I believe that's your theta 3. Let me double check. Yeah. Where is, okay. No, that I was right the first time. Forget what I just said. It's your theta 3. We'll write OP for open. And then you have, I just want to be really sure I'm not messing this up. So your theta 4, yeah, is basically this. Or else you can extend the line up here. I think this is how they draw it in the example, but that's the congruent angles. Okay. So honestly here for this question, they kind of don't solve it with any of the super specific questions from the book, super specific equations, I mean. They really just solve it with law of cosines. So they have like, they draw this line here and then they break it into 2 different triangles that share this red side, and then they kind of do a system of equations to solve for everything here. So this is all just rearranging law of cosines. Okay, so for the open circuit, the only differences between the open and the closed circuit is they're writing, yeah, like Stone says. Stefan asks if Dr. Nader would be okay with solving this with a protractor. Dr. Nader doesn't have a preference of how you do it. I don't think he really checks your work as long as you get the same answer. And Stone says he doesn't see Dr. Nader giving us a question like this, which I think I agree with. I don't know, this question is kind of like a, I don't want to say like an exception, but it's just kind of a weird case. Okay. So ultimately they just kind of solve through law of cosines and they get all their different thetas. The RBs is just going to be this vector, which to solve algebraically, or I guess it's not algebraically, it's through vector addition. You would just solve those two. Once you, at this point, you kind of know your thetas. Honestly, I would just kind of draw it out and use some trigonometry if you're asked a question like that on the exam. But yeah, otherwise it's a pretty difficult question. I would say you would have some simpler questions. Is it okay if I walk through this question, or does anyone have another question they'd like me to go over? Okay. So I'd say this is probably a more standard question. Also, all these questions, they ask you to plot the displacement and stuff. You're not going to have to do that. They're all just doing it with the program. I'm only going to be solving, going over solving the positions and stuff. So again, they just kind of give you the dimensions of all your links. So remember your length D is basically always going to be the link between your like your origins, I guess. Link 2 dimension is A. Link 3 dimension is B. And then that's 4 is your C. So we're actually given all of these dimensions. So if you want to draw it out geometrically, you can. If you can do the geometry for that. Otherwise, we're just going to ignore this coupler point P for now. Let's just focus on finding our theta values of just a regular 4-bar. See if I can pull up. I do side by side like this. Okay, can you guys see my split screen right now, kind of? Okay. So for scrolling through our chapter 4 equations, no. You can see we just have a basic 4-bar here. So they are using the vector method here. Zoom out a little bit. Okay. So you can see they're basically just using the same equations and plugging the numbers in. First you solve for your k constants, and then you'll solve for a, b, and c, which is just, again, kind of just plugging it into your calculator. And do make sure if you're solving this to like write down the steps at each point. Don't try to like, get all your k values and like all your a, b, and c values without writing them down, because I would say calculator error is going to be one of your biggest nemesis here. You can also program this into your calculator. I think Dr. Nader was really pushing for that. However, some of these equations, like, do you really need to type d over a, program that into your calculator? I feel like it's a little overkill, personally. Kiara is asking, how would you program it into the calculator? So it's on your graphing calculators, you can actually make programs. It's kind of a lot to get into now, but you can basically code it. You can code the logic in, so you can like, well, you have to do it either all like through typing it into your calculator. Yeah, Stone says you can look it up on YouTube. You can also, you can get this program like from Texas Instruments where you can code it on your computer and then upload it to your calculator. I'm sure you could probably also maybe find someone who's already uploaded it online and upload it to your calculator. But I feel like, honestly, you know, we've used calculators for enough years. You can do a couple functions on your calculator. Okay, so once we found a, b, and c, then it's again, we're just kind of plugging it into the equation. It's a little weird here because they'll write like a of theta 2. They don't actually mean a. I can't even highlight it. They don't mean like a times theta 2. They just mean a at like a of angle theta 2, a at angle theta 2. Same thing for the b of theta 2. You're not actually just multiplying everything by theta 2. So then they're just kind of going through the same inequality. If it's greater than 2 pi, subtract 2 pi. That's basically saying if you get an answer of like 370 degrees, just subtract 360 to get 10 degrees. And then to find theta 3, again, we're scrolling down to this kind of second set of equations. So we find our next set of k constants and our next sets of d, e, and f. Again, just plug it into the equation. It's kind of just plug and chug. It's just good to kind of draw it out first and get a good understanding of what it might look like. So to Stefan's asking if these questions will be with the equations. Yes, you'll get all these equations on the exam. Let's see if I can pull it up. Dr. Nader actually has if you go to FAQ, frequently asked questions, he has the 2 formula sheets here. And I think I don't know if he gives you both of them, but I think mostly just the first formula sheet is for chapters 2, 3, and 4. The second one is more for like 5 and 6. But these will be, it'll be locked on browser, but it'll have a link to the formula sheet, so you should be able to, I think, open it. Otherwise, if you want to print it out, I think Dr. Nader said that's okay. If you just want to have like paper you can put your hands on, if that makes it easier for you. Yeah. So again, finding the R components, you're just doing vector addition. So they break it into like the I and the J components of your A, which is like your X and your Y basically. And then they do the same thing for P. Honestly, I feel like a lot of the time these vectorial methods, you can also kind of just do it geometrically. If you have all the angles, you can just draw out your, it all just ends up being triangles. You can draw out your triangles. You know, you might have to find the X and the Y components using your trig and stuff with the angles. But like in this problem, if you're given, you have all these angles here, right? And you know, I mean, you know all the lengths of these. Oh, let's see, why did they? Oh, I'm sorry, I drew this wrong the first time. They actually, this isn't length 3. This is length 3. Usually they'll be simple enough that you can do geometry. I would wager to say. So it looks like we only have 10 minutes left. Does anyone have any questions they'd like to get in? Does anyone have any problems they've been looking at that they just don't understand that they'd like me to try to explain? Okay, otherwise I will, you know, this is a good toggle position question. Let's just do that then. So they kind of just give you the lengths here. So the very first thing we want to do if we're given the lengths is we want to calculate Grashoff. So these are a lot of digits to write out. Actually, oops. I'm writing with my mouse pad. So I will just do this in my calculator really quickly, see if it's correct. So short plus small, so I'll have 0.86 plus the long is going to be 2.22. That's 3.08. Then the others are, I guess they're the same thing. So the short plus the longest are not less than or equal to. So it's greater than. That means it's non-Grashoff. So if you remember to our toggle position question, that means this is actually a good thing. We can just solve it as a triangle. So they've really drawn it out here. You have your link A, and then they put the B and the C collinear, and your link D. So you take B plus C, and that's equal to one side of your triangle. A is the other side, and D is your third side. What do we want to calculate first? Calculate angle of link O to A. So I guess they're just asking for theta 2 here, right? So theta 2, we can set up law of cosines, right? So if we scroll down, so we know, so we're looking for I guess we're looking for this angle, right? Say we're looking for C, and we know all the sides. So we can say theta 2 is given on the diagram. I think this diagram here, I don't think this is given in the question, because yeah, I think they just give you the angles, the link lengths, yeah. If it has toggle position, it is always non-Grashoff. I don't know about that. Honestly, I'd have to review. You usually talk about toggle positions more for non-Grashoff. I'm honestly not sure if Grashoff could have toggle positions, unless maybe you define them a little bit differently as maybe like the extremes. But usually when you're talking toggle positions, you're talking like a Grashoff, or a non-Grashoff, I mean, pardon. So is it okay if I don't set up law of cosines here? It's kind of just a lot of writing. I'm sure you guys know. You're gonna have B plus C squared basically is equal to A squared plus B squared, the length of this length, the length of this length, minus 2 times this length times this length, cosine this angle, and then you just solve for that. Yeah, you'll rearrange, and you'll do inverse cosine of whatever you get. So it says the other toggle angle is the negative of this. Honestly, I would usually just kind of draw this out again. So if you look at this and you just think like, if you think symmetrically, you know, these angles are, it is going to end up being, with the same length, it's going to end up being symmetrical. So it's a weird color. Whatever theta you get here is going to be negative theta, or basically going the same theta, just clockwise instead of counterclockwise. Okay, and then here, what are they solving for? They're solving just for theta 3. So, sorry, there's a lot of stuff on my screen to move around with Zoom. Oh, sorry. They're then just solving these same, using the same equation. So, yeah. Again, I think it's pretty straightforward. Maybe just go through a couple more of these questions on your own, just to kind of get familiar with your calculator and going through the steps. Otherwise, these are usually pretty simple of calculating the positions. So honestly, I'd be ready for a lot of conceptual questions too, just because of the nature of online testing. Dr. Nader, it's easier for Dr. Nader to give a bunch of like conceptual questions. So I can post, I can make a PDF out of these notes and these problems that I went over today. I'll post these in an announcement too. And the recording of this session will be uploaded onto web courses too. It'll take a little bit of time to like for it to process and for me to upload it, but I mean, it should be up in like probably an hour at tops. And otherwise, your test's on Thursday, so you still have, I actually don't know what time your class is on Thursday, but you still probably have almost 2 days to study. I won't have office hours this afternoon because of this. Stefan is saying everything is multiple choice. You will have, I think you'll have some fill in the blank questions too. So be prepared, like if it'll ask you like the length of a link or the position of a link, be prepared to like solve through these questions and then type in whatever answer you get. These questions are, I mean, these tests are a little hard too, since I don't think Dr. Nader is doing partial credit. So be really careful with your calculator. Don't lose all the questions. Don't lose all the points just because you like typed the wrong thing into your calculator. Yeah, you won't have to like upload any drawings though. I can pretty much guarantee that. That's for the later drawing test. So no office hours this afternoon, because we kind of did that now, but you can come in on Wednesday, or actually don't know when your test is on Thursday. If the office hours are before the exam, feel free to come in and ask some questions, or just message me on web courses. Okay, otherwise, any other questions or anything anyone wants to say or ask? Okay, if not,